All right, all right. We finally made it to the fundamental theorem of calculus. Remember, we've said calc is all about how fast things are changing and how much they've changed so far. And the fundamental theorem of calculus is the link between those two big things. So how fast things are changing, that's basically the derivative, right? How much they've changed so far, we haven't exactly said yet. It seems like it's probably related to integrals. But let's define something new called the cumulative change so far function. Or you could abbreviate to say the cumulative area so far function, or you could call it the cumulative area function if you really like that area metaphor for keeping track of changes. So we want to say starting at a particular time or location, which we'll call A, and often A is 0, like starting at time 0, but not always. Let's add up all these box areas where each box area is the height times the width, and that will tell us how much things have changed so far. So if we said starting at A, and we'll say maybe f of t dt, then how far do we, what do we mean by so far? When is now? We often think of now as t, but if I'm already using t here, I can't put t in the upper end. That would be like a for loop that said for t equals a to t. That might run forever, or it might stop immediately depending on the programming language. So we have to use some other letter here that says where to stop, kind of when is now, and then t is going between our starting point and now. So we could use a letter x, and we could say the total amount by time x is the integral starting at t equals a going to t equals x of f of t dt. So it's actually not a bad idea to say where is t starting and stopping. Desmos won't understand this notation, but that doesn't mean you can't understand it. So we could write it this way, or we could flip t and f and say integral a to t f of x dx, which would be the integral from x equals a to x equals t f of x dx. Really, it could be any letters. You can use whatever letter makes sense. You can use emojis, whatever you need to. But you just can't say f of x equals integral a to x f of x dx. So let's write that. Not big F of x equals integral a to x f of x dx. Our variable of integration cannot be the same or cannot appear in the upper limit or the lower limit of the integral. So let's go talk about some examples of the cumulative change so far function. So let's define a function here. It might be a velocity, so 0.2 meters per second, and let's start at time 3. What's the definition? By definition, what is f of t dt? We could remind ourselves f of x is the integral from a to x f of t dt. So what's the integral, what's that cumulative change so far, cumulative position change so far, if this is velocity, at time 3? It would be the integral from 3 to 3 of 0.2 times dt, and that seems a little silly, but those 3's are coming from different places. This 3 is coming from what we said is our ending time, and this 3 is our starting time, so that's our a value. And what is this integral? Let's draw it out. Here we are at time 3. Here's our function value at 0.2 meters per second. This is in seconds. And what is that integral? The integral from 3 to 3, that would be a box that is 0.2 meters per second tall and starts at 3 and ends right at 3. So basically a box of 0 width. So the area would be the height times the width, which would be 0.2 times 3 minus 3, which is 0. And what do the units work out to there? It's meters per second times seconds, so it would be meters. So if we start at time 3 and stop at time 3, how far have we gone? 0 meters. Let's do it again for 3.5. So go ahead and write out what the limits on this integral must be. Right, so it's again starting at time 3, stopping at time 3.5, 0.2 dt, and we're starting here at time 3, going over to time 3.5, 0.2. So what's that area? 0.2, 3.5 minus 3, which is 0.2 times 0.5, which is what, 0.1? So if we're going at 0.2 meters per second for half a second, we go 0.1 meters. So let's write it out here again. What's this integral? So hopefully you said it's from integral from 3 to 5, 0.2 dt. So starting at 3, going over to 5, 0.2. So again, you get 0.2 times 5 minus 3, which ends up being 0.4 meters, right? This is 2, that's 2. All right, and then how about 3 to 5.1, 0.2 dt, same basic picture. So we'd have a height of 0.2, a width of 5.1 minus 3, and so that'd be 0.2 times 2.1, which would be 0.42 meters. Now here's where life gets interesting. What if I asked about f of -1? Maybe it doesn't have to make sense. Maybe we'll just follow the system we have so far. So what integral would you write there? So our cumulative change so far function always starts at a, or in this case 3, and then whatever number is there, we put it there. Even though it feels like we're integrating backwards, we kind of are, but it's good to follow our formula. So what's going on there? We're saying from 3 back to -1. So what's our cumulative area so far? It'd be 0.2 times -1 minus 3, which is 0.2 times -4, which would be -0.8 meters. So let's see if that ends up making sense. Let's copy our answers here. At 3, f of x was 0. At 3.5, it was 0.1. At 5, it was 0.4. Here it was 0.42. Here it was -0.8. And I'll kind of sketch a graph to begin with, but then we'll go do it in Desmos more carefully. At 3, so here we have capital F of x. We had 0. At 3.5, we had 0.1. Say that's 0.1. Out here at 5, we had 0.4. And then we had 0.42 at 5.1. And then where does the -1 fall? It would be over here at -0.8. Something like that. And what shape do you see there? Well, maybe you don't trust my by hand drawing. Let's go do it in Desmos. All right, here we are in Desmos. I've defined my function that I'm integrating or taking the cumulative change so far. I've defined my starting point. I've defined my cumulative change so far function. And I've entered the x values we just used on paper, and we're getting the same x values from what Desmos is doing for that integral, so that's nice. And let's show what's happening there, and those are the red dots. So I'm going to grab the upper end of an interval here, and as I drag it along, you can see this blue curve is showing me how much total area I've seen so far starting at A. Does it make sense that that's linear? Every time I move over a little extra chunk, I add the same size value to that blue line, so it's increasing at a steady rate. By the time I get to 3.5 on the axis here, f of x has gotten up to 0.1, like we said. So as I sweep out more and more area, I'm adding up bars that are all the same size, so my total area so far is increasing linearly. And then what happened when we went backwards? Now I'm sweeping out bars that have the same height but a negative width, so my total area so far is decreasing as I move backwards. Usually we talk about decreasing and increasing as we move forwards, but here I'm literally moving backwards. So we can see our total area so far is getting more and more negative as I sweep out more and more negative area. So that's an example of the cumulative change so far function, and let's go talk about that in another video.